Part one of the Introduction to Amateur Astronomy lecture series is entitled Our Place Among the Infinities. So if you're a fan of Robert Frost, especially the poem The Star Splitter, that's where the title comes from. So you might wonder, why aren't we starting with more amateur astronomy type stuff like learning how to read a star map, identifying the constellations, or binoculars and telescopes, the other parts of the series? And there's a story I always tell at the beginning of the series, and here it goes. So many years ago, probably 20, 25 years ago, the Kalamazoo Astronomical Society was doing one of its public observing sessions at the Kalamazoo Nature Center. And somebody brought a very nice telescope, a Meade 12-inch classic LX200. Very nice telescope, probably $3,500 back in those days. It'd probably be more expensive today if Meade were still around. But he needed help setting it up, which is totally fine. But then we slewed it to M8, the Lagoon Nebula. And then he looked at it through the telescope and took a look at it. And then the next person took a look at it. And so that person asked the owner of the telescope, what are we looking at? And the guy said, I have no idea. So that really bugged me because one of the things I think every amateur astronomer should have is a basic knowledge of 101 astronomy. You should basically have a really good idea what you're looking at. Because a lot of the times, the things that we look at through a telescope or binoculars, or even with the naked eye, they're really faint and fuzzy. But when you look at them with your mind's eye, with the knowledge you have in your head, it gives it a lot more meaning. So if you don't know what it is you're looking at, it kind of, I think, loses its charm. A lot of people like the mystery, but when you know what it is you're really seeing, it makes it that much more special. So that's why I begin with this kind of crash course in the basics of astronomy. So here we have a wonderful shot of what we call the Milky Way. And if you were an absolute beginner, you might wonder what this band of light is across the sky. Of course, this is a nice time exposure with your naked eye from a dark sky site with no moon. It looks like this pearl gray river of light. And you might wonder, what is the Milky Way? What is it? And quite simply, this is the disk of our home galaxy as seen from within. And if you don't know what a galaxy is, we'll of course get into that later today. So this is the disk of our home galaxy, the Milky Way, as seen from within. And yes, from a dark sky site with no moon, it is a spectacular sight. But unfortunately, only about 1/3 of all people around the world, can't see the Milky Way. They can't see it at all because of light pollution. And this includes 80% of Americans, because especially if you're east of the Mississippi, light pollution is rampant. When you get kind of out in the west, it gets a little better here and there, or at least maybe up into the UP of Michigan. But for the most part, most people around the world live in cities, and so they never get to see the Milky Way, which is one of the grandest sights of all astronomy. I mean, it's right up there with total solar eclipses and aurora, if you can see it as it was meant to be seen from a dark site. Now, what if we could travel above the disk of the galaxy? Because, of course, this is the disk of the galaxy seen here. What if we could travel far, far above it and look down at it? Because here we see it kind of edge on because the galaxy is flat and we are inside. So this is what it would look like from far, far above, a view that we will never, ever have. We'll never have a view like this of the Milky Way, not a real one anyway. So this is the most recent version of what our galaxy probably looks like. This is from the Gaia probe, which was from the European Space Agency, that basically made 3 trillion, with a T, 3 trillion observations of 2 billion stars. And it basically used all that data, all that tremendous amount of data, to create this artistic representation of what our galaxy probably looks like. It's a little different from the version I used to use in here, but overall, it's very, very similar. So here we have a labeled version of our galaxy, and if you can just make it out, here's this label for the sun right there. Of course, you really can't see it amongst all billions of stars in the galaxy, but we live in what's called the Orion arm, or sometimes referred to as the Orion Cygnus arm. So roughly about 2/3 from the galactic center, or about 28,000 light years, you find kind of a humdrum star called the sun. And we pretty much always call it the sun, but it does have a name, Sol, Sol. So solar system basically means the family of the sun, but the sun is at the center. And more or less, the sun is the solar system, as I'll describe. So a few basic facts here. The distance to the nearest star, which is called Proxima Centauri, a little bitty red dwarf star, smaller and cooler than the sun, is about 25 trillion miles away, or 4.2 light years. It takes the sun about 240 million years to complete one orbit about the galactic center. That's a pretty easy calculation to do. We can talk about that later. The length of its day you can see here varies. This is because the sun is not a solid object, but it's basically a big ball of plasma, the fourth state of matter. There's liquid, solid, gas, and plasma, which is a very hot, electrically charged gas. So it's not a solid object. So it rotates faster at the equator than it does at the poles. This is called differential rotation. So at the equator, the sun spins around once in about 25 days. As you get closer to the poles, it's about 34, 35 days. And yes, the sun is the largest physical object in the solar system, nearly 866,000 miles. You could fit 109 Earths from side to side across the sun's disk, or 1.3 million Earths inside of its volume. And you can see its mass is pretty staggering here, 332,946 times the mass of the Earth. But here I think is a more amazing statistic, is the sun is 99.86% the mass of the solar system. The sun is the solar system. Everything else, including little old Earth, is just bits of leftover debris from its formation 4.5 billion years ago. Isn't that amazing? 99.86% the mass of the solar system is the sun. And so it has a composition of mostly hydrogen, nearly, roughly 74% hydrogen, about 25% helium, and other trace elements that astronomers call metals. When you get beyond hydrogen and helium, which is what was made in the Big Bang about 14 billion years ago, they call everything else a metal. Even though it's not metal like oxygen, but it's just generically referred to as a metal. It's kind of a slang term in astrophysics. And deep down in the sun's core, it's a staggering 15 million Kelvin, which is 27 million degrees Fahrenheit. And that's the temperature you need to fuse hydrogen into helium. And so the sun converts 4 million tons of its mass into energy every second. And this is just to balance the crushing force of gravity. Now, the view we have here of the sun is in the ultraviolet. And of course, it's very sped up. It's not quite this active. Boy, it would singe Earth in no time. But if we go to a more familiar gaze at the sun, we have this one. So this is what the sun would look like with a regular white light solar filter over the front of the aperture. Now, it looks very yellow here. The colors are probably a little artificial. The sun does look kind of yellow in the sky, but that's because of the effects of Earth's atmosphere. If you were to go above the atmosphere, into orbit or something like that, the sun would look white, completely white, not yellow at all. So the color here is maybe kind of an exaggerated version of what it looks like to us in the sky, but I'm sure the colors have been enhanced here a little bit. So this part of the sun is called the photosphere, which is basically the surface of the sun that we can see. Photo meaning, to see. And so the surface has a temperature of 5,800 Kelvin, nearly 10,000 degrees Fahrenheit. And you can see it looks a little brighter in the center and a little dimmer along the edge. This darkening along the edge is called limb darkening, and that really shows you that the sun does not have a solid surface, but it has like these layers. And so, as we look toward the center of the sun, where it's really bright, we look deeper into the photosphere, where it's a lot hotter, and we kind of look at a more shallow angle along the edges to where it's a little cooler, so it looks darker. So these dark regions are even cooler, and these are called sunspots. So the average sunspot is still pretty hot, about 4,000 Kelvin, or roughly about 7,000 degrees Fahrenheit. And about 95% of all sunspots appear within 30 degrees of the sun's equator, as you can see in the image here. And they basically occur in groups and pairs, as you can see. The average sunspot's about the size of Earth, but many of the sunspots here this day are quite large. And right now, as we record this in January 2026, we're probably just past solar maximum, where we have lots of sunspot activity. So you can see lots of big sunspots on the sun like this right now. So basically, what is a sunspot and how do they form? So basically, you have rising and sinking gas currents that twist magnetic fields into rope-like tubes, which tend to float upward. Because remember, Earth has like a global magnetic field that's generated from deep beneath the surface toward the outer core. But with the sun, you have magnetic fields everywhere. Yes, you do have one big global magnetic field, but you also have little magnetic fields strewn all over the surface. Let's see if I can get that to play again. I'm not sure I can get it to play again. We'll just kind of back up there and we'll do it again. So there we go. So you have magnetic fields everywhere. And so where these magnetic tubes burst through the surface, it inhibits convection, because right below the photosphere is the convection zone. You have rising and sinking gases, rising hot gas, sinking cooler gas. And so these magnetic fields inhibit convection. It causes that area to cool off, and we see it as a sunspot. And sometimes you can see there, the magnetic fields can snap and release what's called a solar flare. So here's a different view of the sun. The animated one was in the ultraviolet. The previous version was kind of visible light. This is a very special wavelength called hydrogen alpha, which is at a wavelength of 656.2 nanometers, or if you prefer, 6,562.8 angstroms. Basically, what that means is this is a tiny portion of the red end of the spectrum. So if you've ever looked at the sun through a hydrogen alpha filtered equipped telescope, it looks very red, even redder than you see here, because again, the color here is artificial. But this layer is called the chromosphere, and it's just above the photosphere of the sun. And that's where all the action is. I mean, sunspots are great to observe, but it's the chromosphere is where you have all the action. You have features like these, or this one up here. There was one like this on eclipse day, kind of a pyramid type shape that was very bright, but it was like down here, if you saw that last year. And so these are called prominences. This is basically where solar material, remember, it's charged. There's free electrons, so it's very magnetized. It rises above the surface with the magnetic field. So this is where the magnetic field is carrying away gases from the sun's surface. And then you have these snake-like features. Here's a really good one here. This is called a filament. But guess what? Filaments and prominences are the same thing. A prominence is a filament on the edge of the sun. A filament is a prominence on the face of the sun. Sometimes when the sun like rotates, say this way, this prominent or this filament moves toward the edge, you can see it turn in to a prominence. So observing the sun in hydrogen alpha is a lot of fun because these prominences can change in a matter of minutes. So here's a great animation of one, or a movie of one. This is real data, so it's not an animation, more like a movie. This is from the Solar Dynamics Observatory during kind of its first light release years ago. So here you can see a prominence rise above the surface due to a really strong magnetic field that are often associated with sunspots. So there we go, our local star, the sun. So now let's go ahead and take a tour of the rest of the sun's family, or the solar system. And we'll start with the first 4 planets from the sun, kind of these rocky planets that we call the terrestrial planets, meaning Earth-like. And so basically, the terrestrial planets all have similar characteristics. They have small diameters, compared to the next 4 planets. They have large average densities because they're composed of metal and rock, or sometimes just mostly rock. They have craters and old surfaces, especially for Mercury, as we'll see. And they all orbit inside the asteroid belt relatively close to one another. So they all tend to have the same basic structure, very similar to Earth. They have an inner core, outer core, mantle, and crust. It's just what makes Earth unique is the crust is very thin. So we'll start from the first planet from the sun, Mercury, which is 0.39 AU. This is a much easier way to think of the distance from the sun as opposed to miles or kilometers. So, Mercury is about 36 million miles from the sun, or 0.93 AU, which stands for astronomical units. And 1 AU is 93 million miles, or 150 million kilometers, which is the average distance from the sun to Earth. So remember, Earth is 1 AU, Mercury is 0.39 AU. So it's like a third the distance Earth is from the sun. And because of the sun's stronger gravitational influence, Mercury whips around the sun once every 88 days. Now we know of extrasolar planets that do it in less than a day. So that makes Mercury seem slow by comparison, but for planets in the solar system, it's pretty quick, which is why it's named after the Greek messenger of the gods, or in this case, the Roman messenger of the gods, because Mercury is the Roman version. And so the length of its day is 58 days, 15 hours, 30 minutes. So it does rotate very slowly on its surface. A little bit bigger than the moon, about 3,000 miles. Tiny fraction of the Earth's mass, about 5.5% of Earth's mass. It does have an atmosphere, really more like an exosphere. It'll temporarily capture gases from the sun, like oxygen, sodium, and hydrogen, and so on. And it's one of only 2 planets in the solar system that doesn't have a moon of its own. And so on the side that faces the sun, the temperature is upwards of 430 degrees Celsius, or 800 degrees Fahrenheit. But because Mercury has no atmosphere, when nighttime finally does come to one side of Mercury, the temperature plunges to minus 180 degrees Celsius, or minus 290 degrees Fahrenheit. And it does have a very high density, 5.44 grams per cubic centimeter, or 5.44 times the density of water. And the reason for its high density, but kind of small size, is 70% of its volume is composed of iron and nickel. So in essence, Mercury is a metallic planet with just kind of a rocky crust. It may have had a thicker crust and mantle, but it probably got blown off by successive impacts, like the one that created Caloris Basin. So Caloris Basin is Mercury's largest crater. It's just this big false-colored region here. And it's about 1,550 kilometers, or 960 miles in diameter, and it formed about 3.85 billion years ago. And you can be sure that it took a good chunk of its crust and mantle with it. So yeah, Mercury does have a lot of craters because there's no atmosphere, no forms of weathering. So craters that form there through impacts from asteroids and comets, they last for billions of years. Now, it does have some other interesting features. One of those are these features called lobate scarps. This one is called Victoria Rupes. So this image covers about 150 miles, or 250 kilometers. So for example, this crater here, which may or may not have a name, I don't know if it does, it's about 26 miles or 42 kilometers across. And so these lobate scarps, they basically formed when the mantle and core cooled, shrinking the planet and kind of wrinkling it up, kind of like a raisin. So the Messenger spacecraft from NASA, which was the first probe to orbit Mercury, it revealed that Mercury has shrunk up to 7 kilometers in its 4.5 billion year lifetime. So Mercury is kind of like the shrinking planet. The moon has some of these features too, but Mercury has them in abundance. It has quite a few of them. Now we'll move on to the next planet from the sun, Venus, often referred to as Earth's sister, which, if it's true, it's more like the ugly sister, because it's a pretty nasty place, as we'll see. So now we're 0.72 AU from the sun, so still closer to the sun than Earth, but further away from Mercury. Now, here's the weird thing about Venus. Notice the length of the year, nearly 225 days. But, and that's pretty reasonable, right? That makes sense because Venus is closer to the sun. But look at the length of its day, 243 days. That's not a typo. The length of the day on Venus is longer than the year. And not only does Venus rotate slowly, but it does so in the opposite direction. So it has what we call a retrograde rotation. And we think this is caused by Venus's dense atmosphere. Basically, solar tidal forces eventually slowed Venus to the point to where it stopped spinning in the same direction as Earth and most of the other planets, and then it reversed direction. So here's why Venus is often considered Earth's twin, is because they do have a very similar diameter, about 7,500 miles, and mass, about 81.5% that of Earth. So that's kind of where it ends. That's where the similarities end. The atmosphere is very different. The atmosphere is quite dense, as we'll see, and about 96.5% of that is carbon dioxide, a greenhouse gas, and then a little bit of nitrogen and other trace elements. And yeah, Venus is the only other planet in the solar system to have no moons of its own. So Venus is very cloudy. It's always covered in clouds. It's like a perpetual Michigan. You know, it's always cloudy. And you might think, as scientists once thought, well, the clouds of Venus must be made of the same thing the clouds of Earth are, right? Which is water vapor. So Venus being closer to the sun, it might be kind of this warm tropical paradise. Who knows? Maybe beneath the clouds of Venus, you could have dinosaurs. But no, sorry. There are no dinosaurs on Venus, I'm sad to say. So what are the clouds of Venus? So they're basically sulfuric acid, hydrochloric acid, and hydrofluoric acid. The clouds of Venus are battery acid, so it is a nasty place. Yeah, there is a little bit of water vapor in there, but it's mostly the nasty stuff. So because of the carbon dioxide, the surface of Venus is 880 degrees Fahrenheit or 472 degrees Celsius. It has the hottest surface in the solar system. The atmosphere is 50 times denser than Earth's. The atmospheric pressure at the surface is 90 times that of Earth. So if you're, say, very wealthy but very stupid, there are plenty of examples of that, and you land on Venus with a regular probe, you would be crushed and melted at the same time. So, I mean, by all means, some of the billionaires do it. Just do it. So it's extremely hot. It's hot enough to melt lead, and it would crush you flatter than a pancake in no time, and then you would evaporate. So the rocks we see here are all basaltic, typical of volcanism. We'll come back to volcanism on Venus here in just a second. All these images, by the way, are from the Soviet era of Russia. So these are all from the Soviet Union back in the 70s and 80s. The top image here in the lower left, that's from Venera 13. This one here is from Venera 9. And yeah, the Soviets had really terrible luck with Mars, but they actually had some very successful missions to Venus. And you might wonder, what could the probe look like? What does the lander look like that took these images? And here you go. So this is a mock-up of Venera 13 that's displayed in Moscow, Russia, which, I'll never get to go see it. And so we have the lander module in the foreground here, and you can see it's built to withstand intense pressure. The shield over the camera was composed of a diamond structure because it's the strongest known substance and it could withstand the intense pressure on Venus. And so this probe would sit in this kind of brownish sphere, and they'd put it in a big rocket and launch it toward Venus. So you put the probe in there and so on. So there you go. So they were tough little things, and they only lasted like 40, 50 minutes or so, which is still pretty impressive considering the hellacious conditions on Venus. Now, if we could strip the clouds away and look at the surface of Venus, something we can never do with amateur telescopes, Venus would look like this. The colors are, of course, artificial. They're based on the Venera images, but these are from the Magellan spacecraft. Okay? So Magellan, which operated in the early 90s, mapped about 98% of the surface, showing details as small as 100 meters. And it did discover there are two highland regions, not really outlines of ancient continents. One's called Ishtar Terra, and the other's called Aphrodite Terra. Ishtar is in the northern hemisphere, and Aphrodite Terra is kind of more on the southern equator region. I believe this is a good chunk of Aphrodite Terra here. So in a way, because we've mapped 98% of the surface with Magellan using radar, we actually have a greater knowledge of Venus's surface than we do the entirety of the Earth's surface, when you include Earth's oceans. So yes, Venus does have its fair share of volcanism, but many of the craters on Venus, or not craters, but volcanoes on Venus are kind of different. They're called pancake domes, but they're all classified as shield volcanoes. They have an average diameter of about 25 kilometers or 16 miles, and the maximum heights are about 750 meters or about 2,460 feet. Venus possesses about 167 volcanoes that are over 100 kilometers or 60 miles across. And the big question for quite some time is, are the volcanoes on Venus active? And there is a recent news release within the past year or two where they did show geological changes on the surface around these volcanoes. So yes, some of the volcanoes are in fact active today. And so now we can say that conclusively. And so because these shield volcanoes are kind of very low elevation, but very wide, they're called pancake domes, but they are classified as shield volcanoes. So here is our home planet, Earth. We won't spend too much time here because, of course, astronomy is the study of everything beyond Earth, but we should know most of this stuff here. We are, of course, 1 AU from the sun, 93 million miles or 150 million kilometers on average. Takes us about 365 and a quarter days to complete one circuit about the sun. We have a 24-hour day. We're about roughly 7,900 miles in diameter. Earth is the densest object in the solar system at 5.5 grams per cubic centimeter. So that's an interesting fact about Earth. We are the densest object in the solar system. Just a little bit behind Mercury, because Mercury, for its size, has a lot more metal. And the atmosphere is mostly nitrogen, some oxygen, some water vapor. And if you're wondering how much carbon dioxide we have compared to Venus, remember, Venus is like 96%. We are 0.039% carbon dioxide. That's it. 0.039%. So if you don't think the carbon dioxide that we're releasing into the atmosphere is affecting our planet, it must stink to be wrong, because you are wrong. Many people have made it political, but let them do that. The facts are the facts. Global climate change is caused by an increase of carbon dioxide from us in the atmosphere. It's a scientific fact, and it's a basic one. Now, of course, the really unique thing about Earth is 70% of its surface is covered in liquid water. We now know it's not the only surface to have a liquid on the surface, but it's the only planet to have liquid water on the surface, at least for extended times. So here's a view of my home state, Michigan. You can tell this is a real image because, it's cloudy. So I am probably somewhere under this little puffy cloud right there, I think, roughly. So that's one of the neat things about Michigan is it does have a very unique, recognizable appearance from the International Space Station. You can see a little bit of it up here. So maybe next to maybe Italy, I think Michigan is one of the coolest places to see from orbit because it has a very unique shape. It looks like a big glove as opposed to a big boot. But that's just a quick look at home. Now we'll go on to our nearest celestial neighbor, the moon, which of course does have a name, Luna, but we always, for some reason, call it the moon. I think we should call it Luna, but oh well, that's just me. So yes, the moon is the nearest celestial body at about 239,000 miles away. And notice the time it takes to orbit Earth and the time it takes to rotate on its surface are exactly the same. So because of the Earth's gravitational influence, the moon is tidally locked in place. So there you go. Now, it only has about 1.23% the mass of the Earth and a pretty low density. So that tells us it's mostly rock. And because it doesn't really have an atmosphere, it kind of does temporarily, but not really what we would call an atmosphere. Features last a long time, very much like Mercury. There's very little erosion on the moon. The biggest form of erosion on the moon is from micrometeorite impacts. That's pretty much it. And because it is mostly rock, with very little geologic activity, I call it the dead rock in space. It's bright, it's obnoxious, it just doesn't do anything. As you maybe grow to love amateur astronomy and want to look at the little faint fuzzies through a telescope like galaxies, you will kind of grow to hate the moon. It's just bright and it's just awful. But I guess we do need it. So it is Earth's great partner in the solar system. This view here, this kind of moon transit, is from the Deep Space Climate Observatory, which took this movie on July 16th from about 3:50 p.m. to 8:55 p.m. Eastern Daylight Time. And the one thing you might notice here is the moon looks a little different from the previous image because this is what we call the far side of the moon, not the dark side of the moon because, look at it. Does it look dark? No. I think the dark side of the moon came from the Pink Floyd album. People just started referring to the far side of the moon as the dark side of the moon. I bet the use of that term in the Pink Floyd album of the same name have a common origin. But there you go. There is the far side of the moon getting plenty of sunlight. So here we have the near and far side of the moon. Of course, the near side has all these dark features called Maria or mare for singular. So here's a mare, and then the plural is Maria. So we do have Maria on the near side, and not really hardly anything on the far side, just lots and lots more craters. And that's because of the Earth's gravitational influence again, which has made the moon's crust on this side pretty thin. So the only form of volcanism on the moon, at least billions of years ago, was through impacts, from asteroids and comets that melted the surface and beneath the surface, and it welled up where the crust was thinner and created the Maria. But here on the far side, the crust is thicker, so the lava couldn't reach the surface and kind of wipe out existing craters. Now, here's an image of the moon by yours truly. So, yep, I snapped this picture of the moon, and it looks a little more familiar here, where you can see the lunar Maria. So, the Jesuit astronomer Giovanni Battista Roccoli was the one that devised the nomenclature for the large naked eye spots and craters in book 4 of his New Almagest, published in 1651. And we still use those names today. So many of the Maria have names of either like weather or kind of emotions. So there's like the ocean of storms. There's the sea of moisture, the say the sea of showers, the sea of tranquility, the sea of serenity, and so on. And we do have many of the craters named by Riccoli. Of course, there's the prominent Tycho crater with its bright ejecta blanket. Copernicus has a nice ejecta blanket as well, followed by Kepler there. And Plato has been kind of filled in with lava. So there we go. Just a quick look at the moon. It is kind of fun to observe, but I wish it were darker. So, of course, only 12 men, including Buzz Aldrin, have walked upon the surface. That may soon change because it looks like NASA is going back to the moon with an orbiting mission, or at least a quick circle around, with Artemis 2 as early as next month. We'll see if it actually happens. But NASA is planning to go back to the moon. I just hope it's not to the detriment of robotic exploration, because I put more value into that than I do human exploration of the moon. So I would like to do both, but I don't want to lose the robotic missions to other planets. So basically, Earth and the moon together are the two great partners in the solar system. All right, now we'll travel beyond the Earth to our next destination, which of course is the red planet, Mars. So now we are 1.52 AU from the sun, where Mars takes about 1.88 years to complete one orbit about the sun. Another interesting Mars similarity to Earth is does have a 24.5 hour day, but it's roughly about half of Earth's diameter, a little more than half, at 4,221 miles or so. It's only about 10.7% the mass of the Earth. And when you look at its atmosphere, roughly 95% carbon dioxide, 2.7% nitrogen, 1.6% argon. It does seem very much like Venus, right? With a large component of carbon dioxide in the atmosphere. But Mars's atmosphere is less than 1% as Earth's. So that carbon dioxide just doesn't really do a lot to raise the surface temperature. I mean, it does, but it's not significant, like anything that we would require. There are traces of water vapor and oxygen as well, but nothing that we could really drink easily or breathe, in terms of the oxygen. And we will mention Mars's two moons here shortly. So in a way, Mars is a hybrid of Earth and the moon. It has similarities to both, but it is a world all of its own. And it does have some geological wonders like Mariner Valley, the grandest canyon in the solar system. So Mariner Valley was named after the Mariner 9 spacecraft that orbited Mars in the early 1970s. It actually still orbits today, but of course it's not functional. So Mariner 9 is basically what helped save the Mars program, because at first it was considered kind of a dead world like the moon, but it's only mostly dead. It's still a pretty lively place in some respects. So the Mariner 9 mission was so successful in saving the Mars program, they named this massive canyon after it. So it's about 4,000 kilometers long, or 2,500 miles long, and it stretches about 19% of the way around the planet. It's 6 kilometers, 4 miles at its deepest, and 200 kilometers, 120 miles at its widest, right about here. So Mariner Valley is 10 times longer, 5 times deeper, and 20 times wider than the Grand Canyon. It is the grandest canyon in the solar system. And for the next geologic feature, you can kind of see them out toward the edge of Mars here on the limb. Those are some of Mars's volcanoes. Again, they're all shield volcanoes like what we have on Venus and a little bit on Earth as well. So the largest over here is Olympus Mons. It's about 25 kilometers or 16 miles high, about 3 times the height of Mount Everest. And then we have the Tharsis Montes, Iscratius Mons, Pavonis Mons, and Eurasia Mons. This is from the UAE Hope Mars mission, the United Arab Emirates Mars mission taken in August of 2021. Of course, we have our own Mars missions. We've had quite a few of them here in the US. Here is Curiosity, which landed in Gale Crater on Mars on August 6, 2012, and it's still going strong. Gale Crater, by the way, is about 150 kilometers or 96 miles in diameter. And here it is before, I believe, a global dust storm was about to nearly envelop the entire planet that year, kind of ruined our Mars watch that year, but hey, what are you going to do? So Curiosity is still going strong today because it doesn't have solar panels to get covered up by dust, but it is nuclear powered. And same goes with its sister probe, or sister rover, Perseverance. So Perseverance landed on Mars in February of 2021 in Jezero Crater, which is about 45 kilometers to 28 miles across. And of course, it had a little passenger called Ingenuity, which had the first powered flights on Mars. The first flight was on April 19th, 2021, and the last flight was on January 6th, 2024, and then it somehow got damaged after that. So it had 71 flights in all, and it was a great help to Perseverance, or Percy, for a while because it could help survey potential targets for it to visit. So we have two great rovers operating on the surface of Mars right now. So yep, Mars does have two moons, Phobos and Deimos, because Mars is the Roman god of war. Phobos and Deimos mean fear and panic, and they are shown to scale in this image here. So Phobos is over 7 times the mass of Deimos, but Phobos orbits only 3,700 miles above the Martian surface. No known moon orbits closer to its parent planet than Phobos. So it actually gets about 6 feet closer per century. And within 50 million years, Phobos will either crash into Mars or break up and form a temporary planetary ring. But if we're still around in 50 million years, I think we can use, tractor beams and tow Phobos to a safe distance. So I think if we have the technology, Phobos will survive. But, that's just speculation on my part. So it does have this really prominent crater called Stickney. But while Deimos here looks a little more subdued, the craters look like they're covered, and they are covered in dust from micrometeorite impacts, much like what grinds up the surface of the moon. So let's move beyond Mars to the asteroid belt, the main asteroid belt, because there are other asteroid belts in the solar system, but the main one is between Mars and Jupiter. And it contains an estimated 1.1 to 1.9 million objects larger than 1 kilometer, or about 0.6 miles. Now, from this graphic, you might wonder, geez, how do we even observe Jupiter from Earth with all this stuff in the way? Of course, the asteroids in the belt here are greatly exaggerated in size. So remember, most are very small, and on average, they're 600,000 miles apart. If you were in the asteroid belt, standing on an asteroid, you would have a hard time seeing another one around you. You'd probably need binoculars or a telescope to do it. And yes, again, many of these objects are very small. The four largest asteroids, Ceres, Pallas, Juno, and Vesta, they're 42% the mass of the asteroid belt. 42% the mass of all the objects here are within four objects. So, yeah, most are just little fragments, basically leftover pieces from the formation of the terrestrial planets. So here's the largest asteroid, and yes, I know it's classified as a dwarf planet, but that designation is, I'll just say it plainly, stupid. So we're going to ignore that. So Ceres is the largest asteroid in the asteroid belt, and it's about 2.8 AU from the sun and orbits once every 4.6 years or so. And you can see some other statistics here. I won't bother to go through all of them. It's roughly in diameter about the size of Texas. Kind of is bland too, because yeah, I've driven through Texas many times, and especially when you go through the Panhandle, it's pretty boring. So, Ceres is maybe a little more interesting than that because it does have some cool features, like little bits of salt that pop up in some of the craters here. These bright spots we now know are salt, not ice, as was speculated. So Ceres alone is 25% the mass of the asteroid belt. It does have a 100 kilometer thick mantle with 200 million cubic kilometers of water. So just beneath this kind of icy or rocky, dusty crust is a lot of water. So this movie was created by the Dawn spacecraft that had a mission from March 2015 to October 2018, but it spent like the first year at Vesta and then its remaining time at Ceres, where it's still in orbit, but it's no longer functional. So here's Ceres, of course, and there's Vesta, which was Dawn's first target. And here are just some of the other asteroids that we have visited in the asteroid belt to scale. Poor little Itokawa here, really doesn't even show up at this resolution. So it's just a little tiny fragment of a pixel there. So most asteroids are probably on the scale of these two here. There are some oddities like Ceres and Vesta and so on, but by and large, it's mostly fragments left over from the formation of the terrestrial planets. So now we'll explore the other two types of planets in the solar system, generically called the gas giants. But we now know that Jupiter and Saturn are kind of different from Uranus and Neptune. So we refer to Jupiter and Saturn as the Jovian planets, the more Jupiter-like planets. So basically, the Jovian planets and kind of to a degree the ice giants, Uranus and Neptune, they have large diameters, compared to the terrestrial planets, but low average densities because they're mostly gas, right? And they orbit beyond the asteroid belt. They're much further spread out. And they also tend to have multiple satellites, especially in the case of Saturn, as we'll see. So we used to think they were all kind of similar type planets, but now we know that Jupiter and Saturn are the only ones with metallic hydrogen and then kind of liquid hydrogen beneath their surface. Jupiter has a great deal of liquid metallic hydrogen compared to Saturn. So Saturn's more liquid hydrogen compared to Jupiter, but Jupiter has a good abundance of both. Well, yeah, the term ice giants can be kind of misleading, but don't think of it as solid ice. We're never going to go ice skating, on the mantle of Uranus and Neptune. For one, the atmospheres are very dense. And number two, it's ice compressed to a very high density where it kind of acts like a electrical generator creating their magnetic field. So it's very different stuff than ice as we think of it. But you can see Uranus and Neptune are a fraction of the size and mass of Jupiter and Saturn. So here's Jupiter. We are now 5.2 times the distance that Earth is from the sun. Out there, Jupiter takes nearly 12 years to complete one orbit. Jupiter has the shortest day, just under 10 hours. It rotates very quickly, and it has the largest surface, or largest diameter, I should say, and surface, I guess, if you think of it as a surface, of all the planets in the solar system at nearly 87,000 miles across. You need about 10 Earths to fit across Jupiter's diameter. And as my past students have calculated many times in my massive Jupiter lab, it's about 318 times the mass of the Earth. Pretty impressive. But we now know of gas giants a bit bigger. And very much like the sun, it's composed of hydrogen and helium that it drew directly from the solar nebula when the solar system formed over 4.5 billion years ago. And it currently has 97 known moons. 16 of those moons are larger than 10 kilometers in diameter, while, doing the math there, 81 are less than 10 kilometers or 6.2 miles in diameter. So Jupiter just has a mesmerizing atmosphere. It's just a joy to watch, through amateur telescopes, but especially with robotic spacecraft. This movie was created by the Cassini spacecraft as it zipped by Jupiter for a gravitational boost in late 2000. So this movie spans 24 Jupiter rotations between October 31st and November 9th, 2000. And here you can clearly see the belts and zones. So the belts are the dark stripes on Jupiter. These are low pressure regions where the gas sinks, while the zones, kind of the wider areas, those are regions of high pressure where the gas is rising. And because of Jupiter's rapid rotation, they're strewn in these kind of stripes that we call the belts and the zones. And of course, amongst the belts and the zones are many interesting cloud features. These kind of white oval features come and go. There's little festoons that hang off the belts. But most prominent of all is this little guy here, well, not so little, the Great Red Spot. So here's a really cool movie of the Great Red Spot by Juno, which is still in orbit around Jupiter. At its largest, it was 3 times the size of the Earth, but now it's maybe roughly a little less than 2 Earth diameters because it has been shrinking over the decades. We don't know if it'll disappear, but it could, because we've been observing the Great Red Spot since about 1831. Many people think we've been observing it since the 1660s, but that was a different spot in the northern hemisphere, while the Great Red Spot is in the southern hemisphere. So the one observed in the 1660s was kind of called the perpetual spot, but that's no longer in existence. So perhaps the Great Red Spot will one day vanish and a new one, maybe in a different hemisphere, will take its place. So you can kind of compare the Great Red Spot to a hurricane, but it's a region of high pressure, not low pressure like hurricanes or, cyclones. Now, this view here looks like it could have been taken from Earth with an amateur telescope, but you see Jupiter as a quarter Jupiter, so you can't have that view from Earth. From Earth, Jupiter is always a full planet, or a gibbous planet, waxing, waning gibbous type thing. But here you can see the 4 moons of Jupiter, called the Galilean moons of Jupiter, and sometimes they vanish in Jupiter's equator because they formed around Jupiter, so they are right in Jupiter's equatorial plane. So they often pass in the shadow, which is, you really can't observe that from Earth, but this is a remarkable sight. So here's a better look at the Galilean moons of Jupiter, first observed by, maybe Galileo Galilei, but also an English astronomer named Thomas Harriot around the same time. So Galileo may not have seen them first. It was probably Thomas Harriot. So you can remember the order of the moons of Jupiter, Io, Europa, Ganymede, and Callisto, by saying, I eat green caterpillars. So, of course, I can't take credit for that. That comes from Jack Horkheimer in his old Star Hustler or later Stargazer series. He's long since passed away. And so the moons get their name from another German astronomer named Simon Marius. He's the one that coined the terms of the moons around Jupiter that we still use to this day. Io, Europa, Ganymede, and Callisto. And they're each really fascinating places, especially the first 2 moons. In many ways, they're more fascinating than the planet that they orbit. So Io, of course, is the most volcanically active object in the solar system. And this is because of its position. It's the innermost of the Galilean moons. So not just Jupiter's gravitational tidal forces, but the other moons pull and tug on Io that helps it melt the interior, and it just erupts constantly. So Io is the most volcanically active object in the solar system, which lots of sulfuric eruptions. And so if you could smell Io, at least near one of the active volcanoes, it would smell like rotten eggs because that's what sulfur smells like when you heat it up. And Europa could be one of the most wondrous places in the solar system. It could be a abode for life because beneath this water ice crust is very likely a subsurface ocean. And if true, if it's a nice clear ocean, it could be more extensive than Earth's oceans. And you can see evidence. You can see these ice rafts where chunks of ice have, like, say, broken apart and drifted, on a liquid object. So Europa is a very exciting place, and we have a probe going there, the Europa Clipper, in the next decade. Ganymede is the largest moon in the solar system. It's larger in diameter than Mercury, just not as massive. And Callisto, speaking of craters, is one of the most heavily impacted objects in the solar system. It has this large crater here called Valhalla. Now we go to the ring wonder of the solar system, Saturn, which is nearly 10 AU from the sun. So notice every time we go to a gas giant, we basically double the size of the solar system. So Saturn is nearly twice the distance that Earth is from the sun. And it takes Saturn nearly 30 years to complete one orbit, maybe closer to 29 and a half years to complete one orbit about the sun. It rotates a little bit slower than Jupiter in about 10 and a half hours. And it's nearly 75,000 miles in diameter. So about roughly, 14,000 miles or so smaller in diameter than Jupiter. But it's only 95 only 95 times more massive than Earth compared to 318 for Jupiter. So that's why it doesn't contain as much liquid metallic hydrogen as Jupiter does. And it does have a unusual amount of hydrogen, which makes it the lowest density object in the solar system. Earth is the highest, Saturn is the lowest. Its density is only 0.687 grams per cubic centimeter, so roughly 70% as dense as water. So yeah, Saturn would float in an ocean if you could find one big enough. And you can't quite tell because you're always too busy looking at the rings, but Saturn is also the most oblate of the planets because it does rotate pretty quickly, so it really bulges at the equator. So Saturn's kind of more egg-shaped than spherical. And yeah, today Saturn has 274 known moons. Most, of course, are very tiny and not visible from Earth. So, of course, when most people think about Saturn, they want to talk about the rings. So here's a fantastic view of the rings as seen from the Cassini spacecraft, which was the first probe to orbit Saturn in the kind of mid-2000s and for the next decade or so. I do miss Cassini. So the width of the main rings is about 70,000 kilometers or 43,000 and a half miles, yet the rings are only about 20 kilometers, 12 and a half miles thick. And basically, they're composed of ice. So what happened perhaps within the last 100,000 years is an icy moon got blasted apart through an impact, or a moon got struck by a large object and got shattered. And because most of the moons around Saturn are composed of ice, it formed an icy ring. So if true, if the rings of Saturn were produced within the last 100,000 years, they're at their absolute peak today for us to enjoy. And it is one of the absolute marvels to see through a telescope, the rings of Saturn. Right now, they're nearly edge on, but in the next couple of years, they'll be more prominent again, and they'll just knock people's socks off. So we'll take a quick look at some of Saturn's moons. These are many of the irregular satellites of Saturn that were basically captured. Prometheus and Pandora help maintain Saturn's faint F ring. You can't quite see it here, but these are two shepherd moons that help structure the rings. Then we just have these two here, Epimetheus and Helene. We'll just kind of mention them in passing. Then we have here Janus, Phoebe, which was Cassini's first target when it came into orbit around Saturn. Hyperion kind of looks like a sponge. Mimas has this unusually large crater called Herschel that's about 139 kilometers across, and the moon itself is only 400 kilometers across, so it has like the largest crater with respect to its diameter object that it's on. And Enceladus is another one of the wonders of the solar system. It's only about 500 kilometers across, or 300 miles, but it's covered in an icy crust, has these unusual features called tiger stripes in the southern hemisphere, and erupting from these tiger stripes are active geysers. So we are very certain that beneath the surface of Enceladus is another subsurface ocean like we find at Europa. So there could be microbial life in the oceans of Enceladus, because we're pretty sure the oceans are there. All this water spewing out from these geysers has to come from some source. So it has got to be a subsurface ocean. There's more evidence than that, but again, we're just kind of hitting the highlights here today. So now we have Dione, Tethys, Rhea, and Iapetus. One side is very bright on Iapetus. The other side is very dark. This is because the dark side plows up material from a dark ring that Cassini discovered around Saturn, much further out than the traditional ring. But the moon around Saturn is Titan. The first thing you can tell about Titan is, look at it. It has an atmosphere. That's very exciting. Most moons are barren and dead, but not Titan. So on average, Titan's about 760,000 miles from Saturn. Takes about 15 days to complete one orbit about Saturn. It's actually larger in diameter than Mercury. Just, again, not as massive. And its density suggests it's composed of a lot of ice, as the other moons of the outer solar system are. Lots of rock and ice, but lots and lots of ice. And it does have a dense atmosphere. It's about 4 times denser than Earth's atmosphere. And pretty much the only reason why Titan can retain an atmosphere is because it has just enough mass and it's extremely cold. The surface temperature is about minus 179 degrees Celsius, or 290 degrees below Fahrenheit. So the gas molecules just can never move fast enough to reach escape velocity. So when Voyager 2 flew by in the early 80s, it really couldn't see anything. Same goes with Voyager 1, because they even took Voyager 1 out of its path to get a closer look at Titan, and that meant it couldn't go on to explore Uranus and Neptune. That was left solely to Voyager 2. But it didn't have the proper filters to cut through all this kind of methane haze. But Cassini did. And what it discovered is Titan is the other object in the solar system with a liquid on its surface. But remember, it's extremely cold here. So cold that water is as frozen as hard as rock. So what we see here are seas of liquid methane and ethane, maybe comparable in size to like the Mediterranean Sea. Now, the Cassini probe had a little passenger called Huygens, and it actually parachuted in the atmosphere to the surface. And it landed on January 14th, 2005. Hard to believe it's been that long. And it actually landed with kind of a splat. It didn't land in a really dry area, but kind of a somewhat soggy area. And we now know it landed in a dried up lake. So here's the images from Huygens as it descended to the surface. You can see the cloudy atmosphere. Then once you get below the clouds, you can see a shoreline here with rivers with tributaries carved by liquid methane, ethane. A little more oblique angle there. And then there it is from nearly the surface, and there is on the surface. So these are like fist-sized pebbles of water ice, and you can tell they're covered with this organic goo that rains down from the surface on Titan. Now we'll go to Uranus, which is often the planet people tell jokes about, but we're not going to tell one today. So Uranus was a primal Greek god symbolizing the sky, and it was discovered on March 13th, 1781 by William Herschel. At first, he thought it was a comet. Then he realized it was something more special. And you can see we are now 19.2 AU from the sun. At that distance, it takes Uranus about 84 years to go once around. And you can see the rotation is a bit slower than Jupiter and Saturn. About 14 and a half times the mass of the Earth. And again, very dense hydrogen helium atmosphere with the methane that gives it its kind of sky blue color. And to date, 29 known moons, which are largely unexplored. It's about a third the mass of a third Jupiter's diameter and about a 20th the mass, which is why it has no liquid metallic hydrogen or really liquid hydrogen, so far as we know. Here's a look at some of the moons of Uranus. The names were chosen from characters and works of Shakespeare and Alexander Pope. One of the most interesting ones that Voyager 2 got a good look at was Miranda, because it looks like someone took Miranda apart and put it back together again, but very poorly, kind of like a Frankenstein monster type of thing. But Miranda was caught in this weird phase between melting and trying to differentiate with the rocks at the center and ice at the surface. So it cooled off too quickly and has this really jagged appearance. It has some of the tallest cliffs in the solar system. But by and large, we don't really have great images of the moons of Uranus because we've only had one brief flyby with Voyager 2 back in 1986. That's it. Hopefully we'll send another mission, an orbiting mission, in the next decade or two, but who knows? Now we're at the edge of the solar system. Our last planet on our journey is Neptune. So now we are a staggering 30 AU, 30 times the distance that Earth is from the sun. And it takes Neptune nearly 165 years to complete one orbit. In fact, since it was discovered on September 23rd, 1846 by a German amateur astronomer named Johann Gottfried Galle, based on calculations from Urban Le Verrier, who really gets credit for its discovery, it didn't complete its first orbit until July 12th, 2011, since we discovered it. So, yeah, Neptune was discovered on paper mathematically before it was ever seen through a telescope. It was the calculations that led to its observation through a telescope. Pretty remarkable. And it does have 16 known moons, but really the only moon of significance is Triton. Triton accounts for more than 99.5% of the mass orbiting Neptune. So Triton is almost certainly a captured object from what we call the Kuiper belt, which we'll take a brief look at here shortly. It's also one of the coldest places in the solar system at 391 degrees below Fahrenheit, or minus 235 degrees Celsius. And in many ways, it's a really fascinating place. I find it more fascinating than Pluto, which tends to get most of the press, because it has these active geysers that create these features on the surface, like these active nitrogen geysers caused by tidal heating with Neptune. Very similar to what happens on Io, just not quite as ferocious as what happens to poor little Io. So yes, just beyond the orbit of Neptune is what we call the Kuiper belt. Basically, it's filled with many icy bodies, and in essence, while the asteroids somewhere deep in here are bits of leftover debris of the terrestrial planets, the Kuiper belt is leftover debris from the formation of the gas giants, because there is a lot more ice than rock in the solar system, so you need a lot of ice to collect enough mass to collect hydrogen and helium from the solar nebula to form the gas giants. And it roughly extends from roughly 30 AU just beyond the orbit of Neptune to about roughly 50 AU. But that outer figure may have changed a bit over the years, but it could go as far as 100 AU. We're not really sure about that yet. And of course, by far, the most famous resident of the Kuiper belt is everyone's favorite former planet, Pluto. You might be thinking, it should still be a planet. Let it go. Let it go, folks. It is not a planet. So now remember, this distance, I should emphasize this time, is the mean solar distance. Pluto's distance really fluctuates. Sometimes it's actually closer to the sun than Neptune, as it was for roughly 20 years from 1979 to 1999. It was considered, it was technically the eighth planet from the sun, while Neptune was the ninth. But now it's, of course, not even a planet. So this distance is the average. It fluctuates by as much as like roughly 20 AU or so. And it takes nearly 248 years to complete one orbit. It has not done it since it was discovered in 1930 by Clyde Tombaugh. And you can see it has a very long day, small diameter. It's 65% the moon's diameter. And Earth is 450 times more massive. And you can say it has 5 moons, but I've always kind of said that Pluto and Charon have 4 moons because, well, we'll explain that here shortly. So when these images were taken by New Horizons in around 2015, they instantly became iconic because Pluto has this large heart-faced feature called Sputnik Planitia. And it was basically caused by a large impact within the past 100 million years or so. I mean, in most high-resolution images I've seen, you cannot find a single crater anywhere in this region. It has completely been smoothed out by a massive impact on Pluto. So before the New Horizons mission got there in 2015, astronomers were looking for a ring around Pluto because they suspected it could have a ring. They never found one, but what they did find was more moons. They found Nix and Hydra in 2005, Kerberos in 2011, and Styx in 2012. But now with Pluto and Charon, they're only like Charon's like a 12th the mass of Pluto, which is very close. They actually orbit around a common center of mass that's between the two objects, like roughly right here or so. So Pluto and Charon orbit around this common center of mass. So they are a binary object. That's why I say Pluto and Charon have 4 moons. It's really a binary body, because that's not the case for Earth and Moon, the Earth and the Moon. So here's a great look at Charon from New Horizons. Again, it's about 12th the mass of Pluto, and it's 1.2% the mass of our moon. And notice its orbital period and length of its day are exactly the same, much as our moon is around Earth. But even more interesting is Pluto, or Charon, is only visible from one side of Pluto. If you travel to the other side of Pluto, you'd never see the moon rise above the horizon. So it's locked in the same place in the sky. It's just it changes position as it orbits as they orbit around a common center of mass. Really unusual object. Really, really interesting too. Just interesting colors. They're a little exaggerated here, but still really interesting place. Now, New Horizons got a look at another kind of more generic looking Kuiper belt object called Arrokoth, and on January 1st in 2019. So this is very likely a contact body, 2 objects that kind of gently impacted one another and stuck together. So this could be what a typical Kuiper belt object looks like. If it came near the sun, it'd be considered a short period comet, even though it's pretty good size for a comet. But, we do know of comets roughly this size here, like Hale-Bopp, for example. So there we go. That's probably your typical Kuiper belt object. Now, much further out than the Kuiper belt is the Oort cloud. This goes from 10,000 to 100,000 AU. Now, 100,000 AU is 1.58 light years. The distance light travels in 1 year, so 1.5 light years. So that makes the solar system, if you include the Oort cloud, about 3 light years in diameter. Now, we do know the Oort cloud exists because long period comets have to come from somewhere, because long period comets are way off the ecliptic, the Earth's apparent motion around the sun, or its motion around the sun, or the sun's apparent path in the sky. So most objects from the Kuiper belt are within the plane of the solar system because the Kuiper belt is kind of flat. It's more like a donut, but it's pretty flat. While the Oort cloud is round. So, for example, back in 1996, comet Hyakutake went right by the North Star, which short period comets can't do because they're within the plane of the planets. So Oort cloud comets can have any inclination and fall from any direction in the sky. So these comets have to come from somewhere, and we think they come from the Oort cloud. But we've never observed any object directly in the Oort cloud, because most objects there are very small, very faint. And again, the Oort cloud is at least 10,000 AU away, very, very far. We'll probably never, ever send a probe there, ever, because we don't know where to send a probe to right now. Now, Eris is really not a Kuiper belt object. It's in a region between the Kuiper belt and the Oort cloud called the scattered disk. It's kind of a miscellaneous category because we don't really know much about the region between the Kuiper belt and the Oort cloud. So Eris is the object that, of course, got Pluto demoted to a, quote, dwarf planet, but it's really a Kuiper belt object. And in a way, Eris is too. It's just it got maybe knocked out of the Kuiper belt, perhaps by Neptune, but it's hard to say. So its average distance is a staggering 67.8 AU from the sun. And it takes over 560 years to complete one orbit. And I hope we get to see what Eris looks like in my lifetime, but it's so far away, I kind of doubt it. I doubt we'll ever get to see what this looks like within our lifetime, unless you're very young. Then you might have a chance. But me, nope. I'll never get to see what Eris really looks like. Now, I have seen many comets in my lifetime. We've had some decent ones over the past couple of years. Last year, we had Comet Lemon, and which I did briefly get to see. But here's Comet McNaught, which was the great comet of 2007. And of course, these are the small icy bodies that, they spend most of their time very far from the sun in either the Kuiper belt or the very distant Oort cloud. But they might get knocked into an orbit that brings them into the inner solar system. And they might form an elongated orbit like this, very much like Halley's Comet. So when comets, or the dirty snowballs of the solar system, because they're composed mostly of ice but some dust and rock, when they are far from the sun, they are very dead and inactive, like kind of Halley's Comet is now. This is kind of roughly where Halley's Comet is now, because it has rounded the sun during its last appearance in 1986, and now it's gradually getting closer to us for its 2020 or 2061 appearance. But as they get near the sun, their volatile compounds, like gases of water, ammonia, methane, so on, they begin to sublimate. They go directly from a solid to a gas, but they form like a very tenuous atmosphere around the comet. But as they get closer to the sun, this coma, as we call it, begins to get pushed back by the pressure of sunlight and the solar wind, and they form a tail. Now, one tail you can see points directly away from the sun, while the other has a bit of a curve to it, and you can tell it's composed of these little tiny particles, mostly of dust. So the tails can be very long or gently curved, but in general, they point away from the sun, and they get very active, and then they kind of die down as they fade away. So here's a comet. This is Comet Neowise. back during the pandemic in like July 2020 when we couldn't organize any events to look at it. So here's a great image of Comet Neowise showing the two classic tails. We have the ion gas tail, which is exactly as it's described. It's basically ionized gas that has been stripped of its electrons. So that gives it its electric blue color. And then we have the dust tail, which is composed of dust particles blown off from the comet, either through eruptions or through interaction with the sun. So the dust tail is heavier, so it tends to trail behind the path of the comet, giving it its curved appearance, very much like Comet McNaught, which came very close to the sun, which is why its tail was so curved, as we saw earlier. And then the head of the comet, where all the tail material comes from, is again called the coma. And deep within the coma is the nucleus, the actual dirty snowball where all this material comes from. So that's your basic anatomy of a comet. And because the ion tail is so light, it's basically just particles like electrons and ions. It points exactly in the opposite direction of the sun. And we have gotten some close looks at some dirty snowballs. Here's, of course, is the most famous one, Halley's Comet, as the European probe got to see it back in 1986. And then we saw Wild 2 in 2004, Churyumov-Gerasimenko, which the Rosetta spacecraft orbited for over a year, and several others, Hartley 2, Borrelly, and Tempel 1. So we have had some close-up looks at comets. Now we'll briefly move beyond the solar system to other planets that orbit other stars that we call extrasolar planets. So an extrasolar planet is a planet that orbits a star other than the sun. Now, today, at least as of yesterday, as we record this, January 16th, 2026, we've discovered 6,210 extrasolar planets around 4,633 planetary systems. 1,041 of those have more than one planet. I believe the record is either 6 or 7 exoplanets around one star. So full-fledged solar systems. Now, most of these discoveries were made by two methods. The most successful one is the transit method, which is what the Kepler Space Telescope used and the current TESS mission uses. They wait for planets to pass in front of their star, kind of like this. The star decreases in brightness ever so minutely, but enough that we can detect the planet's existence. So most planets have been found through the transit method. Another method is called the radial velocity method. Basically, as the planet orbits its star, the star kind of wobbles back and forth, and we can detect that motion through the Doppler effect in the star's spectrum. Very similar. So now let's go ahead and travel beyond the solar system to the stars. Now, in this really great image from the Hubble Space Telescope, you can see some basic characteristics of stars. Of course, they have different brightnesses, but that may be largely caused by their distance. Close stars look bright just because they're close. They may be faint just because they are far away. But I believe many of these stars are in the same cluster, so this is a pretty good comparison of their brightness relative to one another. And you can see they also have different colors. So red stars are the coolest. Blue stars are the hottest. Now, the absolute best way to learn about stars is to study what's called the Hertzsprung-Russell diagram. So this is a diagram created in roughly 1910 individually by Einar Hertzsprung and Henry Norris Russell, again in the early 20th century, but they eventually, merged notes and created the HR diagram, as we call it in short here. And it's basically a graph of basic, temperature versus luminosity. Sometimes temperature versus absolute magnitude, for example. There are different versions of the HR diagram. So on our x-axis here, we have temperature. And you can show it as either its temperature in Kelvin, its surface temperature in Kelvin, going from roughly 30,000 to 3,000 Kelvin here, or its color, because a star's color and its surface temperature are interchangeable. So O-type stars are the hottest. They look blue. B-type stars are kind of bluish white. A-type stars are kind of a light blue white. F-type stars are white. G-type stars are yellow. K-type stars are kind of yellowish orange. M-type stars are pretty red. Little variation in there. Of course, again, I mentioned the sun looks white from space, but these are kind of how they look, at least through our atmosphere. But blue stars are pretty blue. Red stars are pretty red. It might vary here and there how a star looks from the surface of Earth as to how it looks in space. So again, we go from hot stars on the left to the coolest stars on the right. Then on the y-axis, here in this case, we have luminosity. Now, luminosity is basically a measure of the energy a star emits per second. And there are two factors that determine luminosity. Basically, it's surface area and temperature. First and foremost is surface area. The larger you are, the more area you have to emit light. So you could have a red supergiant and a red dwarf star down here. They might have the same temperature, but they have very different luminosities because of their surface area. So Betelgeuse is very bright by comparison to DX Cancri down here at the bottom, for example, or more familiar, Proxima Centauri, or if you're a Star Trek nerd, Wolf 359. There you go. So, for example, the sun is a G-type star, and each of these spectral classes, O, B, A, F, G, K, M, have a subrange from 0 to 9. So a G0 star is hotter than a G9 star, and the sun is a G2 star. So the sun's right about here at 5,800 Kelvin. This luminosity scale is compared with the sun. So when you compare the sun with itself, it has a luminosity of 1 in solar units. So that's why we have 1 here. So we go straight over and down to the G's, and you can see there's the sun right there, a G-type star that has a luminosity of 1 when compared with itself. So this is where we find the sun on the HR diagram, on this band called the main sequence, the most important part of an HR diagram. So because stars spend 90% of their lifetime on the main sequence, fusing hydrogen into helium in their cores. So that's what stars spend 90% of their life doing, fusing hydrogen into helium in their cores. That's what the sun's doing right now. So it's a main sequence star, which is why in its spectral type, G2, it has the Roman numeral V after it for 5, but Roman numeral V. So the sun's a G2V type star because it's a main sequence star, where stars spend 90% of their lifetime. So that's what these stars do. And basically, as you move up the main sequence, you increase in mass. So mass kind of goes this way. The lowest mass stars are over here. The highest mass stars are up here. And you can also see we have solar radii. So the largest stars are up here, and the smallest stars, if you really can't call them stars anymore, are down here. But here we have the main sequence stars. So you can see many similar stars to the sun, like Tau Ceti. Alpha Centauri is the exact same spectral type as the sun. So Alpha Centauri A is a G2V type star as well. I think just a little bit older, as I recall. I may be wrong about that, so don't quote me on that. And then we go down to the red dwarfs down here, again, like Wolf 359, Proxima Centauri. And these are the most common type of stars in the universe, because most of the stars near the sun are red dwarfs. And even though, like, for example, Proxima Centauri is only 4.2 light years away, it is not visible to the unaided eye. That's how feeble red dwarfs are. But the advantage is they're very small, they consume their hydrogen fuel very slowly, so they basically last forever. No single red dwarf anywhere in the universe has died of old age. Maybe they got, pulled in the black holes, but that's another thing. altogether. So all stars down here, they're less massive, less luminous, and thus smaller than the sun. As we go up, the stars get hotter and more luminous because they're larger in diameter. So, Spica and Virgo, that's a pretty powerful star that we see in the sky. But stars don't spend forever on the main sequence. Again, only 90% of their lifetime. Medium mass stars like the sun, they'll become giants. They'll basically expand into much larger versions of themselves. So Arcturus is what the sun may look like, roughly 4 billion years in the future. It'll really expand, and as it expands, it cools. So we have giants up here. These are stars that no longer fuse hydrogen into helium in their cores. They may be fusing helium into carbon and oxygen. Then we go to the supergiants. Now, this is the fate of only the most massive stars, like way up here. So supergiant stars are about a lot more rare than giant stars. So there are some familiar ones in the summer, like Deneb, or Antares, but in the winter, we have, of course, Betelgeuse or Betelgeuse and Rigel. And, you can see Polaris is also in the supergiant phase. So it's no longer a main sequence star. Now, giant stars will eventually shed their outer layers, and the core will collapse into what's called a white dwarf. So the sun's here, it'll eventually kind of go over here, then its core will go down here. So your position on the main sequence is not constant. You don't stay there forever. Now, of course, roughly 1/3 of stars in the Milky Way are part of binary or multiple star systems. So roughly 2/3 of stars like the sun are single. Now that statistic has changed a lot, and you see variations out there. I saw recently online that some people say 85% of stars are part of binary or multiple star systems. And some still use the old term that I learned when I was growing up, where roughly half the stars in the sky are part of binary or multiple star systems. But I think most astronomers say 1/3 of the stars are binary today. So the sun really isn't that unusual when you look at it, at least that way, if it's true. So binary stars are very important because they allow a direct measurement of a star's mass, which can help us test our theories of stellar evolution, how stars evolve over time. Stars do, of course, come in larger groupings like open clusters or galactic clusters. You can use both terms, but most people use the term open cluster. Why, I don't know. Galactic cluster makes more sense because it tells you where the cluster is in the galaxy, in the disk of a galaxy. So these are basically a collection of 100 to 1,000 stars in a region about 25 parsecs in diameter. A parsec is roughly 3 light years, let's say. And they have some interesting characteristics. They're relatively young. They're typically 200 million years old or younger. They have circular orbits within the disk of galaxies, mainly spiral galaxies, and they're what we call metal rich. They are composed of mostly hydrogen and helium, but they have roughly 1 to 3% metals, stuff beyond hydrogen and helium on the periodic table. Here we have 2 clusters together. The big one here, the really kind of sparse one, this is M35 in the constellation Auriga. It's about 2,800 light years away and has 500 members. This is NGC 2158, which is about 11,000 light years with over possibly 10,000 members total. But you don't quite see that many in a telescope. So I personally think they're a lot of fun to observe through a telescope. Not everyone loves to observe open clusters. They consider them rather sparse and dull. But it depends on what open cluster you're looking at. Like the double cluster, that's a lot of fun to observe. Now, of course, admittedly, much more fun to observe are globular clusters. These are collections of 10,000 to 100,000 stars or more, in some cases, in a region about 10 to 30 parsecs in diameter. By and large, they're located in the galactic halo, which is this cloud that surrounds the Milky Way, this cloud of stars around the Milky Way. I'll show you a visual here shortly. Now, there is one exception to this, for example, M71. The globular cluster M71 is in the disk of the galaxy, and it always stays in the disk. So that's very unusual for globular clusters. By and large, they're in the halo. Now, these stars are old. They range from roughly 5 to 13 billion years old. Only a handful of open clusters last maybe 4 billion years. M67 is one example. But globular clusters, by and large, are much older. So they formed at a time when there was very few metals. So they are metal poor. They have maybe 0.1% the metal content of stars like the sun, maybe 1% for the more richer stars and globular clusters. But they're considered metal poor because when they formed, the universe didn't nearly have as many metals in it because the metals come from supernovae and stuff like that, as we'll see later. Now, this here is the grandest of the globular clusters. This is Omega Centauri. So if you've ever gone to like the Winter Star Party or the Texas Star Party, like I have, those are the only places I've got to observe Omega Centauri, and it is awesome. It makes M13 really pale in comparison. So this thing's about 86 light years across, and it's about 15,800 light years away, and it contains upwards of 1 million stars. It's probably the halo of an ancient galaxy the Milky Way absorbed. So here we see a diagram of the Milky Way. So of course, here's the disk where we live. So there's the sun, about, again, 2/3 from the galactic center, roughly 28,000 light years, as we mentioned earlier. And we have the central bulge, where we have a supermassive black hole that I'll mention later. And then around the halo, around the bulge, is the halo. And you find a lot of old red dwarfs in that region, or maybe some white dwarfs. But the most best known citizen of the halo are globular clusters, like Omega Centauri or M13, just not M71. It's in the disk. But you do find lots of open clusters in the disk. You pretty much exclusively find open clusters in the disk of the galaxy because they're so young, and most star formation occurs in the disks of spiral galaxies. Now here we see a very familiar sight, probably the most popular constellation. Maybe more people know about the Big Dipper, but as we'll discuss next time, the Big Dipper is not a constellation, it's an asterism. So this is probably the most popular constellation, Orion the Hunter, where you see 3 stars in a row, 2 above and 2 below. But hanging from his belt is a wondrous group of stars and one interesting object called a nebula, specifically an emission nebula known as the Orion Nebula. So emission nebulae are very special. They have a very popular nickname called stellar nurseries. These are the places where stars are born. So here's two views of the Orion Nebula. This one shows the Orion Nebula and the Running Man Nebula, both part of the same complex, so they're really part of the same cloud. They just are divided by this dark nebula here. And this is with an amateur telescope. This, of course, is with the Hubble Space Telescope. And you can see, again, this group of stars in the center called the trapezium. And so in this region, the mass is estimated to contain enough material to create 10,000 sun-like stars. And there is an extremely young cluster in the Orion Nebula that you can see in infrared views, not like here, that's maybe only 300,000 to 1 million years old. And about 300 stars are currently emerging from this cluster. They're much more obvious in infrared view. But we'll kind of zoom in to this central region here called the Huygens region. And this is like an open cavity, this bright, sharply defined central cavity at the heart of the Orion Nebula. And here we see the trapezium, basically this kind of quadruplet system, kind of a cluster in a cluster called Theta Orionis. So Theta Orionis is really a multiple star system, or again, a cluster in a cluster called the trapezium. It consists of 8 separate components, A through H, and possibly a 9th, X, that has only been observed twice by Edward Emerson or E.E. Barnard in 1888 and 1889. If anyone spotted it with the Hubble Space Telescope, I haven't heard about it. So the brightest component is Theta 1c, this one here. And it It's actually a binary system. So Theta 1 Orionis C1 is an O6V type star, very powerful main sequence star, 33 times the mass of the sun. And C2 is a B0V type star with 11 times the mass of the sun. And we believe the trapezium stars here, the four together, are about a third of a light year apart. So they help illuminate the entire nebula. And you can see little dots of gas here, or dust and gas here. Those are regions where solar systems are in the process of forming. We call those proplyds, or protoplanetary disks. So these are the places where solar systems are being formed. Although if you're too close to the trapezium, they might strip all the gas away before planets have a chance to form. But some studies show they form a lot faster than we think they do. So here's where you have all four types of, or all three types of nebulae together in what we call the Trifid Nebula, or M20, which is about 4,100 light years away. It does have a cluster as well, a very young cluster, less than 400,000 years old, and it's about 15 light years across. But in this region, we see the pink emission nebulae, where the gas is excited from hot stars, from ultraviolet light from hot stars. It's actually the gas is actually giving off its own light because it's excited by absorbing all those photons from these hot stars at the center. But then there's dark nebulae, basically dark clouds of dust and gas that, just basically absorb light because they're thick and there are no stars nearby. And it's this dark nebula that divides the Trifid up into three basic parts that gives it its name. And sometimes there's basically a lot of gas, or more dust than gas, that reflects starlight. And that's where we have a reflection nebulae around the Trifid here. So this is a reflection nebula where the dust particles are very small and can only scatter blue light because of its short wavelength, while the pink nebula gives off its own light, and the dark nebula doesn't do anything. It just absorbs or blocks light. So again, this is another region of star formation. Stars here are very young, and some are still in the process of forming. Now here is stellar roadkill. This is the exact opposite. This is a planetary nebula. This is a dead star. Now, planetary nebulae don't have anything to do with planets. It's just that at low power, in small telescopes, they look like little disks like Uranus. There's some famous ones like the blinking planetary in Cygnus. It looks like a little blue disk like Uranus. That very much looks like a planet. But the ring nebula here, it looks like a donut through a telescope, or of course a ring, hence the name. And so the ring is about 0.9 light years in diameter, while the outer halo in this deep image from Hubble is about 2.5 light years across. And it's about 2,300 light years away. So this is a medium mass star like the sun that has died. Probably a bit more massive than the sun, but still in the medium range. And this is the ultimate fate of the sun in about 5 billion years. So these are the fates of the giant stars. The really short version here is when giants form, they gradually expand and contract over time. If you want the long, drawn-out version, please read the companion notes that accompany this lecture. There I go into much greater detail. But every time these stars expand, they release layers of themselves. And you can see that in the previous image here. These are the layers of the old star that have been ejected, like we see in the movie here. And eventually, at the center, if you saw it in the previous image, is what we call a white dwarf. Very small star, about the size of the Earth, but much higher in density. A teaspoonful would weigh about 15 tons because the matter is so compressed because of the crushing force of gravity. And these white dwarfs are very hot. The one at the heart of the Ring Nebula is about 100,000 Kelvin, so it gives off a lot of ultraviolet light, and it excites the gases that ejected, and they glow. So that's what we call a planetary nebula. And this is the fate of most, stars, especially the medium mass stars. Red dwarfs don't do this though. They just kind of gradually, fade away when they eventually do, which they haven't yet. So here is something that obviously blew up. This is the Crab Nebula and the Horn of Taurus the Bull. And it's about 10 light years in diameter and contains about 5 solar masses in all. We believe the progenitor star had an estimated mass of 8 to 13 solar masses. So this is the fate of the most massive stars. They eventually, their cores suddenly collapse into neutron stars or black holes, while the outer layers implode and rebound in a terrific supernova explosion. So planetary nebulae take maybe hundreds of thousands of, if not millions of years to form. Supernova remnants like M1, the Crab Nebula here, form very quickly. And we know this one became visible on July 4th, 1054, because Chinese astronomers saw it, and so did some Native Americans in the Southwest because they drew, pictures of it below rocks, out west. So here's like a supernova explosion in the process of occurring. The only difference here is supernovae can remain bright for over a year. The Crab Nebula was visible to the naked eye for like a month in broad daylight, but it was visible at night for over a year. Then eventually it faded from view. But they do occur very quickly, and then they'll expand and gradually fade, where this material will get eventually recycled into the interstellar medium. Now, the heart of these things are either one of two things, either a neutron star like this, or perhaps a black hole. Now, neutron stars are very fascinating. They're even more extreme than white dwarfs. Now, again, white dwarfs, they're about the diameter of Earth, but have the mass of the sun. And so these are objects with the size of a city, but the mass of the sun. So they are incredibly small, but extremely dense. So they're only about 10 kilometers in radius, 20 miles in diameter, and have a density of 10 to the 14th grams per cubic centimeter. Remember, Mercury and Earth had 5 grams per cubic centimeter. These things are 10 to the 14th grams per cubic centimeter, like 100 trillion times the density of water. And a sugar cube size would weigh about 100 million tons. And they have magnetic fields 1 trillion times stronger than the sun. And they, some of them rotate very rapidly. Most of them do. But if these beams of radiation from the magnetic poles sweep past the Earth, we see it as a pulsar, like beams from a lighthouse hitting you. So here's a movie of the Crab pulsar. This star, which again roughly has the mass of the sun, spins around once every 33 milliseconds. And if we could point a radio telescope at it, it would sound something, I gotta turn my laser off, like this. So it sounds like a broken car that needs, some muffler work, but that was like the beams of radiation striking the radio telescope. Now, of course, if the core of the star has maybe more than 8 times the mass of the sun, it doesn't collapse into a neutron star. It collapses into a black hole where its escape velocity exceeds the speed of light. So it forms an event horizon around a singularity, and sometimes objects fall into it. And if objects fall into it, then it emits X-rays, and that's how we can detect some stellar mass black holes in space, because you can't find a black hole by itself because they're black. And the only way you can find them is if they exert a gravitational influence on a companion, or they have they're in the process of eating the star and give off lots of X-rays. Now we'll move on to galaxies here. So basically, a galaxy is a collection of stars and gas and dust, and they come in a variety of sizes. The best way to understand the different types of galaxies is to study the Hubble tuning fork, or as it's more officially known as, the Hubble Galaxy Classification Scheme. But, it's more fun to call it the Hubble tuning fork because, looks like a tuning fork. So on the handle, we have the elliptical galaxies. So elliptical galaxies are very much like globular clusters. They're composed of very old stars that are metal poor, and there's really no star formation within them. And they do come in a variety of shapes. We basically determine the number after E, which of course stands for, you guessed it, elliptical, by this equation here. So we basically do a little math here. We measure its diameter and its height, and we plug that into a calculator. So if A and B are equal, this is 0. So you're an E0 type galaxy, which means you're very spherical. So the larger the number, of course, the more elliptical you are. And then you get in, well, of course, first here is an example of an elliptical galaxy. This is like, one of the most largest galaxies we know of in the universe. This is M87, sometimes referred to by its radio source name, Virgo A. And this galaxy is at the absolute heart of the Virgo cluster, the nearest large galaxy cluster to the Milky Way. It's about 53.5 million light years away, and its brightest portion is only about 120,000 light years across, which, is pretty comparable to the Milky Way. But remember, it's spherical, so it contains many more stars. But if you include its extended halo, which you can kind of get a sense of in this image, it's about 490,000 light years across. It contains about 2.7 trillion stars and has a whopping 12,000 globular clusters. And at the heart is a supermassive black hole that's 3.5 billion times the mass of the sun. And of course, we've gotten a look at that black hole. This is kind of like the shadow of the event horizon. Not really the event horizon itself, but this is called M87 star, the supermassive black hole at the heart of M87, or Virgo A. And the Virgo A comes from the jets of radio jets here. They do emit visible light, but they give off strong radio signals as well. And that's where the name Virgo A comes from. Because, and like that animation I showed earlier, black holes can give off jets as they're eating material because they can't pull it in all at once. So many galaxies like the Milky Way and M87 do contain supermassive black holes at their hearts. So as material gets pulled off around them, they orbit in a disk. And then because the black hole can't take in all the material at once, some of it is ejected in jets that shoot out into space at relativistic speeds, like 15, 20% the mass, the speed of light. It's really incredible. So now we go on to SO galaxies, or lenticular galaxies. Now, lenticular galaxies are like spiral galaxies in their structure, at least in every way. They have a central bulge and they have a disk, but the disk has no spiral pattern. So they're kind of like really flat elliptical galaxies. They seem like they're an evolutionary middle, but we're not quite sure why lenticular galaxies are why they are. Now, they do have some gas and dust, as you can see in this one here called PGC 10922. So there's probably a little bit of star formation going on here, but by and large, like other elliptical galaxies, they don't really have much in the way of star formation in their disk, which is why you don't really see much in the way of bright stars and evidence of star formation. So now we'll go off into the spiral galaxies. Now, we'll start with the regular spirals. So if you're an SA galaxy, your spiral arms are very tightly wound. If you're a SC galaxy, then your spiral arms are very loose and open. So SBs are intermediates. So here's an example of a nice regular spiral galaxy. This is Bode's galaxy, or M81, in the constellation Ursa Major, not too far above the bowl of the Big Dipper. This one's about 11.8 million light years away. It's about 90,000 light years across. It does contain a 70 million solar mass black hole. And it's also classified as a grand design galaxy because it has two very symmetrical spiral arms with not much in the way of spurs and branches. There's kind of one here, but overall, it's a very symmetrical galaxy. And only 10% of spiral galaxies are grand design galaxies like this one. And as you can see, unlike lenticular galaxies, there's lots of evidence of star formation. I mean, look at all that pink emission nebulae and some bright young blue clusters that come from those emission nebulae. So this would be like an SA type galaxy, very tightly wound arms. Now, here's probably an SC galaxy. This is called the Fireworks Galaxy, NGC 6946. And it gets its name because, on average, you're only supposed to have one supernova per century in a galaxy. But this one has had 9 supernova in the past 60 years, maybe 70 now. But you get the idea. This thing has had an unusual number of supernova within the past century or so. This one's about 22.5 million light years away, about 75,000 light years in diameter. And again, you can see this one has multiple arms and branches and spurs, and about 60% of galaxies are multi-arm galaxies like this one. So the remaining 30% are kind of woolly or flocculent galaxies, but I don't really have a picture of one here today. But you can Google woolly galaxy or flocculent galaxy, and you can see a picture of one. So now we go to the barred spiral galaxies because from the central bulge, they have a bar of stars and dust and gas and clusters, and emanating from the end of the bar are spiral arms. So if you're an SBA galaxy, you're a barred spiral with tightly wound arms. If you're an SBC galaxy, you have a barred shape with very loosely wound arms. And again, SBBs are intermediate barred galaxies. So here is the textbook of barred spiral galaxies, because in pretty much every textbook I've ever seen, and I've seen a lot in my day, this is the image they show when they talk about barred spiral galaxies. So it is literally a textbook barred spiral galaxy. This is NGC 1300, which is about 61 million light years away and 110,000 light years in diameter. Now, 2/3 of all spiral galaxies are barred spirals. And that includes, of course, as you might have saw earlier, the Milky Way. So here is a different view of the Milky Way galaxy. Now, it's considered an SBC galaxy with loose arms, but I've always thought of it as more intermediate compared to other galaxies, but it's classified as SBC, so okay. And as I kind of hinted earlier, galaxies are not isolated. Like stars, they are grouped into clusters. So some clusters are what we call poor galaxy clusters, where they have maybe 20 to 100 members. But then there are rich galaxy clusters that have thousands of members, like the Virgo cluster, or especially this one here. This is like a super rich galaxy, Pandora's cluster, as seen by the James Webb Space Telescope. This is actually the merging of 3 galaxy clusters into one super galaxy cluster. This one's about 3.98, or really, let's just say 4 billion light years away in the constellation Sculptor. Yeah, it's billion with a B. And kind of unusual here is all the matter you can see, all the stars and gas and dust that make up this thing, that's only 5% the mass of the cluster, what we call baryonic matter. You know, what we think of as regular matter that surrounds us and what we are made of. And if you could view this with an X-ray telescope, you would see it surrounded by hot hydrogen gas. That's also baryonic matter, but in a gaseous form. That makes up about 20% the mass of this cluster. The remaining 75% of the mass of this cluster is this mysterious thing called dark matter. We're pretty sure it exists because of its gravitational influence, but it doesn't emit, absorb, or otherwise interact with EM radiation like, light. So dark matter is still a mystery, but we're very certain it exists because of its significant gravitational influence. So a rich galaxy cluster. Now, here's a poor galaxy cluster, and this is the local group of galaxies, the galaxy cluster the Milky Way is part of. So at present, the local group contains about 55 known galaxies. Of the bright galaxies, 14 are dwarf ellipticals, considered the most common type of galaxy in the universe. 3 or 4 are spiral, because many astronomers consider the Large Magellanic Cloud here a satellite galaxy of the Milky Way to be another barred spiral galaxy. So 3 or 4, depending on your view. And then 4 are irregular type galaxies, of the bright ones anyway. So we put the Milky Way at the center because we're the ones making the map. So we just do that for reference. But the center of the local group is kind of between the Milky Way and probably closer to Andromeda. But nearby Andromeda is M33, the Triangulum galaxy. This one's about 2.4 to 3 million light years away. It's about 60,000 light years across, contains 40 billion stars. And as far as we can tell, this one does not contain a supermassive black hole, which is really very unusual. Now, of course, here is the flagship galaxy of the local group. Sorry, it's not the Milky Way. It is the Andromeda galaxy, M33. This one's about 130,000 light years in diameter, or if you include the fainter extended parts, about 220,000 light years in diameter. It contains 100 trillion stars compared to 200 to 400 billion for the Milky Way. It's has a mass of 1.5 trillion solar masses, 850 billion solar masses for the Milky Way. And it contains a supermassive black hole of 100 million solar masses compared to 3.5 million for the one in the center of the Milky Way. So to wrap things up here, let's take a little ride. We'll start with the sun. Let's say this is the sun, 2/3 from the galactic center in the Orion Cygnus arm. And here we go. So we can see the large and small Magellanic Clouds. As we move out from above the disk of the galaxy, we see some other fainter galaxies in the local group. There's the Andromeda galaxy in M33. So here's the local group. Again, a very poor galaxy cluster. Just 55 known galaxies. And now we can see another galaxy group here. This could be the M81 group with the galaxy M81. That's the nearest galaxy group to the local group. It contains about 34 known galaxies. So in a way, it's even poorer than our local group. So the local group fades from view. There's the M81 group. Now we pass right through a rich galaxy cluster. This could be the Virgo cluster, about 54 million light years away, with about 2,000 members. Now, eventually, we'll move out really quickly here. It's kind of sped up here in a second, and we'll see that the Virgo cluster and the local group and M81 are part of what we call the Laniakea supercluster of galaxies. Now, the Laniakea supercluster contains maybe 300 to 500 galaxy clusters and about 160 megaparsecs in diameter, 160 million parsecs. Now, there's some indication the Laniakea cluster really isn't gravitationally bound, so that would mean we are still part of the local supercluster. And now the Laniakea supercluster is part of the Pisces-Cetus supercluster complex. It's 1 billion light years long and 150 million light years wide. And so these superclusters are connected in long filaments and walls of superclusters of galaxies, as we see in the image here. This is the large-scale structure of the universe. So finally, let's take a look at our place among the infinities, or another way you can refer to it is our complete universal address. So you can put your name at the top if you want, then your address, your city, state, or province, your country, your continent or island that you live on, your hemisphere, east or west. So some of us may differ on that. The one thing we all have in common is we live on Earth, which is in the solar system, which is part of the Orion arm or the Orion Cygnus spiral arm. which is part of the Milky Way Galaxy, which is part of the local group of galaxies, which is either part of the Virgo supercluster lobe, or perhaps just the Virgo supercluster, or the local supercluster, or if it's not, if it is gravitationally bound, the Laniakea supercluster of galaxies, which is part of the Pisces Cetus supercluster complex. That is the galaxy filament that we live in, and that is part of the universe. So there is your complete galactic address. So that concludes our place among the infinities.